Right. Hey guys, can you guys hear me today?
You're good.
Thank you. All right. And people are piling in pretty fast. That's good. Hey, how come some of you guys can just get in and others are put into a waiting room?
Because some of us have already made an account with Zoom, but what UT wants us to do is go through their feature. So if you click sign in with SSO, meaning sign in with some school organization, it gives you like the UT version, which is different, I guess. Even like I originally made my account with my UTE ID stuff already, but then I think I had to delete that account in order to go through UT directly to access Zoom, if that makes sense.
Yeah.
Yeah, it probably means that those people are using their personal email addresses, and they made like
Yeah, probably
sent out a notification saying that we had to use the EID ones.
Yeah, we had to use the account that UT made for us already.
Okay. Well, they set it up, and I cannot change this default now. They set it up so that students who don't do whatever it is they wanted students to do get stuck in a waiting room, and then I have to admit them. At least once I do admit the first people, then I can set it up so that everybody else is admitted automatically, but it's kind of annoying. I mean, and I know why they do it. It's this whole Zoom bombing problem.
Well, that, and they think they're trying to make the connections as secure as possible, because I think they're trying to like encrypt the connections.
Yeah, well, there's several problems here. I mean, there's always some jerk out there who can just try to join a meeting that they don't belong to, and then they put up some, racist thing or porn thing or whatever, and that disrupts the meeting. We also are having some bandwidth problems. People are starting to notice that now that the entire country is trying to Zoom through their classes and business meetings, it's not working out as well as it might have if we didn't have to use so much bandwidth. Any other like technical problems that you guys need to tell me about or ask for help with? The communications or the YouTube or the Piazza or anything? Hey, of course, one of our other electronic components to the course is the Quest homework, and I got to tell you, I looked carefully at it now, and the homework that I set up for you guys is, I took a homework from a previous semester and just recycled it, but it doesn't match our timetable right. So you may have noticed already that because I did it yesterday or today, the due date on the next homework is now not until the 15th, not the 8th of April. And the reason for that is that the material that we have up through today will just be enough for you to get through, I think it's the first 6 questions on the homework. All that other stuff about doing integrals in other coordinate systems like polar coordinates or using other transformations, that's what we're going to get to next week. And so you can relax a little bit. You don't have to do that stuff right away. I mean, you're welcome to try it, of course, but we'll be getting to it starting, probably not today, but starting on Monday, we should be able to talk about those other more complicated things to do with integrals besides the ones that we're doing. But did you have any questions on like those first 6 or so questions that I think you do have the tools for? Does anybody want to ask me about any of that stuff? No? Okay. We have some other twists and turns to the whole Fubini's theorem route that we have to go through. And in particular, that has to do with, well, 2 topics in particular. One is I need to show you what happens when you try to reverse the order of integration. So just to recap, what we had out of Fubini's theorem was that Mr. Fubini gave us a way to take an integral that was presented as you're trying to integrate over some region in the plane, and you are presumably chopping that region up into little bits and multiplying the area of each bit by the value of a function of 2 variables somewhere inside that little bit. And that's fine for the sort of the conceptual and for getting the integrals set up in the first place. But then when you actually go to compute it, you'd like to be able to use your techniques from Calc 1, and that requires writing your integral as a succession of two one-dimensional integrals. Then a question that always comes up is, do you have to put x on the inside and y on the outside, or whichever way I did it for you before? And the answer is no, you can do them in both orders. But what I want to show you today is how you can use that facility to actually make your life easier, because here's the thing. If I give you a surface integral to compute, I mean an integral over some portion of the plane, yeah, you can write it as an iterated integral, two one-dimensional integrals, but you can do it in either order. You will get the same answer, but there's no guarantee that doing it in the one order or the other is necessarily equally easy for you. So it's to your advantage to be able to write these integrals out in different orders. And I want to show you that by doing an example just to get all of that stuff clear. So let me swing this around, turn it into my document camera. A little fuzzy earlier today. Let's see if it can be a little more clear this time around. How do I orient this thing right? I have all these degrees of freedom and I can't seem to get them to my advantage. All right, here's the third. So here's a classic problem. Suppose that I ask you to compute a double integral. So it's an integral. It would typically be written this way. You see some numbers over here, and you see some functions over here, and then another function to integrate with respect to x on the inside and y on the outside. Hey, by the way, can you do me a favor? Don't say x first or y first or whatever, because the words first and last are used in different ways in different parts of the problem. I'll show you in a few minutes. So get in the habit of referring to this as saying that you have the integral of, with respect to x on the inside and y on the outside. So this, you'll see this integral written down in a lot of science books, engineering books. People just write out their double integrals like this. But I find that that's a little unhelpful, at least when you're not used to dealing with these things. It's more helpful to put in a few extra bits of decoration. In particular, I like to have the square brackets, or I don't care what shape of brackets, so that it helps you focus on the integral that you're doing on the inside, and then you know that at the end of the day, all of this stuff should be replaced by some function of y that you then integrate with respect to y. And when you do that, these limits of integration will refer to values of y, whereas by contrast on the inside, you're integrating with respect to x, and so these limits of integration should refer to values of x. So I would prefer if you write those double integrals with all this additional notation that I just threw in. There's nothing wrong with the way that it was, but it's perhaps possible to confuse you guys. So Fubini's theorem says that this kind of thing can arise when you have an integral that has to be done of well, it's the same exact function. There's a function of two variables. If you don't see a second variable, that's because it doesn't really matter. But somebody was asking you to integrate some function of two variables over some region in the xy plane, and then you used Fubini's theorem on it, and I told you last time how you would get the region of integration, sorry, you would get your limits of integration from staring at your region of integration. And then, if you had used Fubini's theorem to change this integral into this one, then all you have to do, and I'm putting quotes around that phrase, all you have to do is to now perform these two integrals, which you can do using the tools you had in Calc 1. You'll find an antiderivative of this function of x, and stick in these two values of x, and subtract, and then all of this will turn into a function of y, which you will then anti-differentiate with respect to y, and you plug in this. So you know how it's going to go. And you happily put down these symbols to get started, because you know you don't change the outer stuff right away. And then you say, okay, fine. Now I need to take this function of x and find an antiderivative so I can stick in these two endpoints. Who's got an antiderivative for me? Ah, yeah, the silence is deafening. So this is a function of x, and we know on general principles that it has an antiderivative. That's actually the fundamental theorem of calculus. But there's no guarantee from that theorem that the antiderivative of this function can be written out at all using the kind of language that you already have. You already know about the trig functions and sine and logarithms and exponentials and square roots and a whole bunch of other things. But there's no guarantee that the set of functions that you already know about is sufficient to describe the antiderivative of this function. This function has an antiderivative. I guess I've seen a name for it, but I don't remember what it is. I do know that it cannot be written out using sines and cosines and square roots and logarithms and everything else. So the attempt to evaluate this double integral by starting on the inside and working our way out is dead in the water from the first step. We can't find an antiderivative, and so we have nothing to put into this big blank space. However, we have another trick that we can use, which is to say, okay, we would have gotten into this position if we had started with a surface integral. Let's go back to that surface integral and use Fubini's theorem again, but this time putting the variables in the opposite order. So I'm going to try to write this as a double integral of the exact same function. There's your same function of two variables, but I'll put y on the inside and x on the outside. So there's still, conceptually, I've still got these square brackets, and I'll have x equals something, because x was on the outside. Here I'll have y equals something and y equals something. And I described for you guys last time how you can fill in these four blanks before you have to start, evaluating the integrals. But my tool for filling these four things in requires looking at exactly what my region of integration is supposed to be. And I don't know what it is, but I can reconstruct it from the limits of integration that were given over here. So I want to encourage you guys to do this. Please get in the habit of saying, if you want to do interchange the order of integration, you certainly can. But the hard part of doing that initial step is finding the limits of integration, which is basically going to force you to draw a picture. You're going to have to describe what this region of the xy plane is, whose limits of integration are being described up here. So let's try that. If I had given you some sort of region in the xy plane and asked you to take an integral over this set, if this is the set S, and I wanted you to take an integral of a function over S and write it as a double integral in this order, so I'll try to see what I would be doing with x on the inside and y on the outside. You know that I would do it with exactly the same function f. I won't write that stuff out. But I would have to get my limits of integration on y first. When you're computing the limits of integration, the variable that's first is the variable that's on the outside. And the way I would have you do this would be to scan the whole set S, looking for the least and the greatest values of the y coordinate that you see anywhere in the set. So you have to kind of wander around within this set, talking to all these points, asking them for their least and the greatest values of their y coordinates. If in this example they tell us that the least y coordinate that you ever hear about is a 0 and the greatest is a 1, that means that this figure can't quite look like what I've drawn here. This figure seems to have y coordinates that are negative. So my picture has to look a little different. It has to consist only of points that are stuck between these two horizontal lines. They all have y coordinates that are between 0 and 1. 0 is the lowest, 1 is the highest. So there should be at least one point that's on the bottom edge and one point that's on the top edge. But nothing higher than this and nothing lower than that. So my region of integration has to somehow look like this now. So this is what I hope is a better picture of what the set S looks like. Now to go further, what I would do to figure out these limits of integration would be, and here's the language that I used with you last time, on this inner integral, you're going to be treating everything that's not an x as a constant, which means the y would be held constant. So I asked you to go to your figure at S and hold the y coordinates constant. And the set of points that have a constant y coordinate make a horizontal line. And then I wanted you to stare just at that horizontal line segment, the intersection of that horizontal line with the set S. And that's the set that you scan, talking only to these points, and you ask all of these points about their x coordinate, and you record the lowest and the highest answers in these two spots. So apparently, the highest x coordinate that I get will be a 1. Every point that I talk to will have an x coordinate of 1. So I'll draw the line where x is equal to 1, and I'll put a dot here, but the fact that the x equals 1 shows up right in this spot means that that's the maximum x coordinate that I would get for any point that's in my set S, and at the same time within my horizontal line. And apparently that's true no matter where this horizontal line is drawn. So what I did for you here was I drew a point that had an x coordinate of 1, but really I should have drawn such a point on that horizontal line, and another one on this horizontal line, and another one on that horizontal line. Apparently, no matter what value I hold the y coordinate to, when I ask the points in that line segment about their x coordinates, the largest x coordinate that I hear about in every single case is x is equal to 1. So now you have an assembly of horizontal lines, every one of which has a dot at on this vertical line, x equals 1. So it seems to me that this has just become the right-hand edge of my figure. This is the bottom, this is the top, and the right is going to be this vertical line. By contrast, the situation is a little different when I talk to the points in one of these line segments and I ask about their x coordinates and I think about the lowest answers that I get, the westmost point. That's the point that has the lowest x coordinate within this line segment. What I've written here is supposed to be that x coordinate. When I talk to my points, apparently the lowest x coordinate that I get for any one of the points is a number that's equal to that point's y coordinate. Now remember, this was a horizontal line where I was holding the y coordinates constant. So when I say this guy's x coordinate is equal to its y coordinate, well, it's the same as the y coordinate for any of these points. But it is the same as the y coordinate for that point. So this leftmost point, the westmost point, is a point that has equal x and y coordinates. That means that it has to be on this line of points where x and y coordinates are equal. This is the line y equals x. When I say it's the line y equals x, the line is a set of points, and every one of those points have x and y coordinates. And to be on this line, the membership test is that your x and y coordinates have to be equal. So the statement that the lowest x coordinate that I get anywhere on this horizontal line is an x coordinate that's equal to that same y coordinate, that says that the leftmost edge of my line segment is going to be a point that's on that slanted line. And that's true about this horizontal line. It's also got to be true about this horizontal line. Okay, so whatever my set S is, it only goes as far to the left as this dot when I'm talking about that horizontal line. And for a horizontal line up here, where the y coordinate is higher, here's all the points where y is equal to 0.9. Apparently on that line segment, the smallest x coordinate that I ever get is an x coordinate that's also equal to 0.9. And so when you darken in all these left-hand endpoints of the line segment, you can see that what you're gathering together is exactly the line y equals x. So the conclusion is that in order for me to have gotten these limits of integration in the first place, the region that I'm integrating over has to look exactly like this. It's a triangle that has as its boundaries the line y equals 0, that's the horizontal axis, the line x equals 1, that's this right-hand edge, and the line y equals x. That's my region of integration. And you can double check it. Go through the process that I gave you guys for how to figure out the limits of integration when the picture is given to you. You have to first talk about the y-coordinates and ask all the points in the entire set about their y-coordinates. And apparently the lowest y-coordinate is 0 and the highest y-coordinate is 1. So that's fine. Then you hold the y-coordinate fixed and you look at the points that are in your set and ask them about their x-coordinates. And you record the least and the greatest x-coordinates that you find. And the smallest x-coordinate is equal to the y-coordinate, and the greatest x-coordinate is always equal to 1. So those are the limits of integration. So to recap, if you need to do an interchange on the order of integration, you may do so, but before you try to figure out what the new limits of integration are going to be, you have to reconstruct the domain. You have to reconstruct the picture of what is the set that you're trying to integrate over. Now that I've got that, I can figure out what these limits of integration are going to be when I do flip the order of the variables. Now I've got x on the outside and y on the inside. So to get my new limits of integration, I have to go through a similar process again. If the process of going from here to here was the backward direction, this is now the forward direction. Let's see how that plays out. So let me draw the picture again. There's my domain. That's the region that I'm trying to integrate over. And it's bounded by 3 line segments, where y is 0, or x equals 1, and where y is equal to x. So we begin on the outside here, and we write down the least and the greatest values of the x-coordinate anywhere inside the set. Low x-coordinates mean going south, high x-coordinates mean going north. So I have to talk to the points that are the southernmost point and the northernmost point anywhere in my set. But let me spend just a minute making this a little bit more detailed. You'll notice that what I just did was I stared at the picture and I thought about what kind of point I'm looking for, the kind of point whose x-coordinate is going to be the winner here or here. And I just darkened in the point that I wanted to stare at, because these are the points whose I'm so sorry, I got that backwards. Why didn't anybody stop me when I drew these little arrows? Let me say that again. Wow. I need the minimum and maximum values of the x-coordinate anywhere in my set. And the minimum x-coordinate is found by going west, and the maximum x-coordinate is found by going east. So I scan the whole set looking for points that have the least and the greatest x-coordinate, meaning the westmost point right there, and the eastmost point right there. We have a tie for the points that are at the most furthest to the east, but just pick one and stare at it. And now, see if you can figure out what the coordinates, what the x-coordinate of this point is and what the x-coordinate of that point is. Now to do that, the point I want to make is when you identify the points that are on the edges that are going to give you your minimum and maximum x-coordinates, you only need the x-coordinate of that point, but usually it's going to be more helpful to get both of the coordinates of that point. These are points in the plane. They have x and y coordinates. Let's figure them out. I mean, it's only the x-coordinate that I really need in both cases, because this guy will report the lowest x-coordinate that I need right here, and this guy will report the highest x-coordinate that I'll need right there. But ask yourself what both of those points are, because if you're looking at coordinates rather, because if you're looking at a particular point, you know that that's a point and it has coordinates. It has 2 coordinates to describe the point. If you want to describe the 2 coordinates of a point in the plane, you're going to need 2 pieces of information to figure it out. So the way to get those 2 coordinates is to write down 2 equations that bind the coordinates of your point. And you get each one of those 2 equations by looking at one piece of information that you know about the point. So this point down here, I might describe it as being the intersection of that line and that line, which means that what makes this point be what it is that it simultaneously has to have x equals 1 and y equals 0. And now I know what the 2 coordinates are for this point. It's the point 1, 0. If, when I had asked you for the eastmost point, and you had darkened in this as your candidate, Well, I would have said, let's figure out two things we can say about this point so that we can figure out what its two coordinates are. And this point I would describe as being the intersection of the vertical line x equals 1 with the slanted line y equals x. Here's two equations and two unknowns, and you can take those equations and actually solve for the two values and figure out what the coordinates of this point are so that they are 1 and 1. All right, let me pause here for a second. We have a question. Nathan.
Did you intentionally put the lower left point to the left of the origin?
No, I mean, it looks like I was being, maybe you thought I was being intentional, but in fact I was being sloppy. But that's okay, because we're going to discover, I'm going to say the same thing about this point here. I mean, in the picture, whether I was sloppy or accurate, if I asked you for the point that has the lowest x coordinate, you would say the lowest x coordinate is going to be the point that's furthest to the west, and you can see in your picture where it is. You can darken it in your picture. To figure out what its coordinates are, I would do the same thing that I've done in these other cases. Write down what you know about that point. You need two pieces of information about the point so that you'll have two equations, and you can solve the two equations to figure out the two coordinates. I would say that this is the point that's on the horizontal line y equals 0, and apparently it's also supposed to be on this slanted line. Well, it doesn't even look like a straight line, does it? But this is the equation that, at least conceptually, I was trying to use to describe that curve. So now here you have two equations that describe the coordinates of this point. Two equations you should be able to solve to get the two coordinates, the two unknowns. And of course, it's obvious that you need your y coordinate, it says, already is equal to 0, and then the x coordinate has to be equal to that. So I've obviously done a very simple one for you guys here, where the two pieces of information are just, you know, a really simple pair of equations. But you could imagine a situation where I would have a couple of curves that are described by some fancy formulas involving x's and y's, which is to say, I would be describing these two curves implicitly. And then if you had the two equations, you could figure out the coordinates from this point by eliminating one of the variables or doing whatever else you need to do to solve two equations and two unknowns and figure out the values of x and y. So yes, they're very simple in this case, but they do lead to what we know should have been the right drawing. I should have been drawing that blob at the origin, because the only point that's on this curve and this curve is the point that makes both of these equations be true. And it doesn't take a whole lot to solve those equations to get this point.
That's the thing that you're trying to explain, that we need two pieces of information because beforehand we didn't know for sure that it would lie on the origin.
Correct. And I'm trying to prep you guys for situations like this, where the boundary of your region is, you know, none of the edges could be one of the axes or even a straight line. And then what are you going to do? So, so I do want you to get in the habit of thinking about the two pieces of information that you know. I mean, when you're staring at a point, how would you describe over the phone? Like, I don't know, a lot of you guys you're not using video today. Maybe you don't even have video. So if you wanted to do a Zoom meeting with somebody else and you had to describe in words what the picture is, you'd have to say, oh, now I'm talking about the point that's where that slanted line meets the horizontal line. And then, okay, your classmate would know the kind of point you're talking about. But when you say that you're on the slanted line, here's a piece of information that you gave me. And when you said you're also on the horizontal line, then there's another piece of information you gave me. And now you got two equations. Go play. Anyway, in fact, I'll do it again in just a minute, because I got more limits of integration to fill in. In this case, the least x coordinate that I see anywhere in the set is the x coordinate of this leftmost point. And I have now decided where that leftmost point is. And in particular, I know its x coordinate. So that's the minimum x coordinate anywhere in my set. I know you guys are not surprised to discover that. As far as the other one over here, I need the greatest x coordinate anywhere in the set. That means I need the rightmost point in the set. We have a tie. We have actually an infinite way tie. These guys are all tied for being the rightmost point. But just taking this one, for example, I found two pieces of information to describe this point. I use those two pieces of information to get the coordinates of that point. And in particular, the x-coordinate of that point is right there. So that's the largest x-coordinate that's to be found anywhere in this set. Now, I've only done half of the limits of integration that I need. To get the next ones, remember that on this inner integral here, we'll be treating everything that's not a y as a constant. So in particular, I'm going to be holding x constant. And the set of points where x is constant is a vertical line. So let me return to the picture. I'll draw the picture fresh here. So this was the horizontal axis. This was the line x equals 1. This is the line y equals x. So now, for these inner limits of integration, I need the least and the greatest values of the y-coordinate, but not across the entire set. Rather, I just need the least and the greatest values that are to be found within my figure that happen to lie on this set of points that have x being held constant. So that means I'm only looking for the y-coordinates among these points here, and I want the least and the greatest values of the y-coordinates among the points on this line segment. Well, you get your minimum y by going south, you get your maximum y by going north. So obviously this is the bottom. That's going to be the point that gives me the minimum y-coordinate, and this is the point that gives me the maximum y-coordinate. And when I say this point right here, well, what am I trying to draw your attention to? What I mean is it's the point that lies on that horizontal line, and at the same time, it's on this vertical line. Now that's two pieces of information. It's two equations that link x and y. And there's not really anything to solve here because it already tells you what your x and y coordinates are. And in particular, your y coordinate is 0. So 0 is the y coordinate of this point, but I can see in the picture that it's the lowest y coordinate that I see anywhere in the line segment. So that's a 0. And now one more time with the two pieces of information gained. What do we know about this point? Well, it's got equal x and y coordinates because it's on this line. And because it's on this line, I know that x is equal to that number c. Two equations and two unknowns, use them to solve to figure out the coordinates of that point. Obviously, it says right here that x is equal to c, and then y has got to be equal to x, so it's that same number c. So the y-coordinate, the greatest y-coordinate that you will see anywhere in this line segment is the y-coordinate of that point, which we just figured out. It's equal to this number c. And what is c again? C is the constant value that we're holding the x-coordinates to as we move from the outside in. Inside this square brackets, x is supposed to be held constant, and c is the value that we're currently holding it to. So c, in this case, it's a synonym for x. It means the same thing as x. So by tradition, we write x in there. And now, I finally have my limits of integration. Observe this much. Every time you try to use Fubini's theorem to go from a two-dimensional shape to the two one-dimensional integrals, your outer limits of integration will always be constants. Those are the ones you figure out first. Your inner limits of integration will not typically be constants. I mean, they might be, but they typically involve the variables that were outside of the integral. So these are usually functions, the way I've set it up here, this would have to be a function of x. All right, well, so great. I used Fubini's theorem to take this double integral back into an integral over a triangle, and then I used Fubini's theorem again to change it back into a double integral. So what have I gained by doing all this work? The answer is that this new integral is easier to do. I mean, when you actually try to evaluate these integrals, yeah, I went from the outside in when I was trying to get the limits of integration, but now to compute the integrals, you work from the inside out. So from the evaluation point of view, now y is the first variable. So I start with y, and I look at this function of y, and I find its antiderivative with respect to y. But wait, inside the square brackets, everything that's not a y is treated as a constant. So all of this stuff is just some constant. And that means that it's very easy to anti-differentiate, because I know how to anti-differentiate a constant function. You just take whatever that constant is times the variable. And of course, now I have my antiderivative, and I'll have to stick in these two endpoints. Y is equal to that constant on the one hand, and it's equal to this other constant on the other hand. Inside the square brackets, I keep referring to x as a constant. So obviously plugging in y equals 0 will make the whole thing just drop out to 0. And when I plug in y equals x, what I get is x times sine of x squared. And that's the function of x that I need to integrate with respect to x. So by the way, you should probably make it a habit to pause at this point in your calculations. When you get done evaluating your inner integral, what you have left should be a function of only the outer variable. There should be no y's remaining in here. There could be plenty of x's, as in this case there were x's involved in the integrand itself, and there were also x's involved in the limits of integration. So that gave me, these two x's showed up for sort of different reasons. But anyway, it's a function of x that remains. So, well, we have another Calc 1 kind of integral to do. Anybody want to suggest a way of evaluating this integral?
Integration by parts.
Oh, good call. Yes, you could do integration by parts because this is a product. That would require that you integrate one of the factors and differentiate the other one. Don't try to integrate this one. Anti-differentiate this one, because that's how we got stuck before when we started the problem in the first place, right? We couldn't find that antiderivative. So you could use integration by parts, but I would propose that you integrate this factor and differentiate that factor. Actually, there's something that's a lot easier. Yeah, use a U substitution in this case. That would go a lot faster. Yeah, so I'll just do it that way. I'll say, let's just let u equal x squared. So then du would be equal to 2x dx, which is almost exactly what I have left over around the outside there. So if I wrote everything in terms of u, the parts that I just underlined are almost the same as du. They're du over 2. And then this other part is just the sine of u. And my limits of integration are, let's see, if u is the square of x, then this u would be 0 squared, which is 0. And up here, u would be 1 squared, which is also 1. And so I pull out the 1/2, and then I just have to anti-differentiate sine of u. I remember that that's negative cosine of u. And when I stick in u equals 0 and u equal 1, I get, let's see, so 1/2 times the negative of the cosine of 1 minus a negative of 1/2 of the cosine of 0. Cosine of 0 is 1, so I could write it a little more simply like this. There. That's my final answer. Just to do what I proposed that you guys should always be doing, and I didn't do it in this case, I did ask you guys to always think about, hey, can you estimate the value, the kind of value that you're expecting for your integral? When I wrote this thing out as a double integral, I realized I was integrating this function over this triangle. The sine of x squared is, well, it's the sine of something, so it's always between -1 and +1. So if the function itself takes on values that are always between -1 and +1, then the integral will be between -1 times the area of this triangle and +1 times the area of this triangle. And of course, you can see that the area of this triangle is 1/2. It's a triangle, a right triangle with the legs of length 1. So I was expecting an answer that was somewhere between -1/2 and +1/2. And sure enough, as it turns out, 1 minus cosine of 1, I don't know what the cosine of 1 is, but it's somewhere between 0 and 1. So this number is between 0 and 1. And when you multiply by 1/2, that gives me a number that's somewhere between 0 and 1/2. So that matches my seat of the pants estimate for what the value of the integral would be. Comments or questions? Okay, so I tried to do this really slowly so you guys would get in the habit. It's not hard but you just have to get used to the pattern, the little patter that I speak to myself as I set up these integrals. When you want to use Fubini's theorem, you have to imagine that you're wandering around talking to points, looking for the least and the greatest values of whatever the coordinate is that you're focused on at that moment. In the first stage, you're looking at the entire set, and in the second stage, you're looking at the portion of the original domain that has the other variable held constant. That's the secret in there. And in fact, you can use exactly the same process to handle a triple integral. So suppose, for example, that I ask you to compute an integral of, I don't know, let's just have x times y times z. There's a function of 3 variables that I'd like you to integrate over, I don't know, how about a cylinder? And I'll take a cylinder that's centered at the origin with a radius of 1 and a height of 2. Okay, so that means that if I try to draw that figure with the axes around it, I'll have the origin at the center, and then the rest of the coordinate axes would be in here. There's the x and the y axis, x and y axes, the z axis up that way. If the overall height should be 2, that means it goes up to a height of 1. So here, this top circle that I just drew is part of the plane where z is equal to +1. The other circle is down here. That's part of the plane where z is equal to -1. And then the other sides, the other edges of the cylinder are, they will be part of the hollow cylinder. This hollow cylinder is the set of points where x squared plus y squared is equal to 1. When you see an equation like this that has no z's in it, then the solution set would be a bunch of points that all have the same x and y coordinate but varying z coordinates. If there's no mention of z in the equation, then there's no constraint on what the z coordinate can be, so you can go up or down and still stay inside the set. And in this case, what I did was I took the intersection with the xy plane itself. I looked at the points that might have z equal to 0, and that would have been one circle. Specifically, it would be, to have a radius of 1, it would be the circle x squared plus y squared equals 1. And if I just don't mention z, then I get an equation that describes that surface of points in 3-dimensional space. So, take that solid cylinder, divide it up into a bunch of little chunks, multiply the volume of each one of them times the value of this function somewhere inside each chunk. So you go chunk by chunk, evaluating this function over and over again, and well, you multiply the value of the function times the volume. That's all I can say. Add all of those up and you'll get some sort of an aggregate of the values of this function times the overall volume of the cylinder. You might want to be thinking about what you would eyeball as the value of this thing before I dive into the calculations. But let's calculate it by using Fubini's theorem. So what does that mean? By Fubini's theorem, I can write this as a triple integral of exactly that function, where I can integrate with respect to x on the inside, y in the middle, and z on the outside, or any other permutation of those variables. Oops, sorry, too many. Sorry, I didn't need this one in here. So when you have 3 variables, there's actually 6 different ways that you could arrange the 3 variables in this problem. You only had two ways to consider in the two variable setting, but now it goes up. It's n factorial, where n is the number of variables. However, I don't need to think too much about that right now, because we won't have time to actually evaluate the integral. What I do want to focus on, though, is setting up the limits of integration. You need to stare at this figure and tell me about the values of the z coordinate. What are the least and the greatest values of the z coordinate that you see anywhere in this set? Anybody want to tell me the numbers to put in here?
-1 and +1.
Yeah, -1 and +1 will do. You can see that as I wander around the entire solid cylinder, if you want the lowest z coordinate, you need to go down an elevator as far as you can, and that would rest you on this bottom plane of points that have z equal to -1. And if you want to get the maximum value of z, pick a point that's on the top floor where the z coordinate is equal to +1.
That does mean, though, that for the minimum and maximum y values for that integral, you have to put it in terms of z, right?
If you have the integral set up with the variables in this order, then yes. The next thing that I'm going to have to do is to hold the z constant and say, oh, now within this square brackets, everything that's not a y, well, inside the square brackets, the z, which is on the outside, is going to be held constant. So now I have to look back at my original picture and say, where are the points in here that have a fixed z coordinate? And then I will only ask those points about their y coordinates, and I will record the minimum and maximum values for those. Now, if you look at the set of points where z is equal to a constant, I've already drawn the ones that have z equal to +1 and the ones that have z equal to -1. In fact, I also drew the ones that have z equal to 0. But I could ask you, where are all the points inside the solid cylinder that have a z coordinate equal to 1/3? And those would be the set of points that's in some lower plane. But fortunately, we notice that no matter what the z coordinate is, as long as it's between -1 and +1, the set of points in that solid cylinder that have that z coordinate, they just form a disk, a solid disk that's centered at the origin and has a radius of 1. So in this particular problem, the limits of integration that I'm going to put in for the y will turn out to be the same for every z. In a more general problem, you would expect that you would have something in here that has z's in it, the same way over here. But like I say, in this particular case, we win because we're going to have, can I say it this way, we'll have congruent cross sections irrespective of which z coordinate we fix at. So now you stare at this disk and you talk just to the points that are in the disk, not the whole cylinder, just in the disk. And you ask all of those points about their y coordinates, and you have to record the least and the greatest values of the y coordinates that you get anywhere in this set. As before, the y coordinates are found by going as far to the south as possible. The minimum y is furthest to the south and the maximum y is furthest north, which means this is the point that's going to give me my least y coordinate. This gives me my maximum y coordinate. What are these points? Well, this one I can see it's on the y-axis. In other words, it has an x-coordinate of 0, and it's on the circle. So it has x squared plus y squared equal to 1. There's my two pieces of information. I've written it as two equations. Two equations you can solve for the two variables. Oops, I'm off the screen here. And to solve for these two variables, I see obviously that x is equal to 0, and the y-coordinate you can tell will be equal to 1. So that's my maximum y-coordinate. In the same way, my minimum y-coordinate is clearly the y-coordinate of this point. This point is on it's on the same circle and on the same vertical line, but the solution of the two equations that applies to this point here is that we have x equal to 0 and y equal to -1. So those are my two limits of integration this time. Then, to move to the next integral, to get these next limits of integration, you now have to hold z and y constant. So you first held z constant, and that forced you within a certain plane. You had only a disk left. If you also hold y constant, now you're down to just a line segment. And within this line segment, you need to know about the least and the greatest values of the x-coordinate. Well, those are points that have y equal to whatever this current y-coordinate is, and they are, as usual, on that circle. So here's your two pieces of information about the x and the y. And if you now want to figure out what the x-coordinate of this is, you simply solve for x, and you get the square root of 1 minus y squared for the first, and the negative of the square root of 1 minus y squared on the bottom. So the concept is not different at all when you're doing a triple integral using Fubini's theorem. It's just that there are more stages. You first look for the minimum and maximum values of whatever coordinate you put out here. And in this case, you're choosing on the entire original three-dimensional shape. Then you hold one of the coordinates fixed. So now you're down to a two-dimensional shape. And you scan that shape for the least and the greatest values of this coordinate. Then you take that shape and you hold another one of the variables fixed. So you're down to just a line segment. And you tell me the least and the greatest values of the remaining coordinate. So you can set up a triple integral using Fubini's theorem, a volume integral using Fubini's theorem as well. It just takes a little longer, but it's not the same, it's not any different concept. All right, comments or questions on this problem? Trying not to go over. Yes, Yang Zhu.
Can you?
Oh, wait, hang, I got a hand up from Yang Zhu.
Okay.
Okay, my question is very simple. So how do you interpret it, this integral? Like, what is the geometric or any meaning for this integral?
Okay, good question. Very good question. Remember that the way you always interpret an integral is that you, for some reason, went all around the inside of the cylinder, constantly evaluating this function and multiplying values of this function times the volume of a piece. Now, why would you ever multiply some function times a volume? I got one answer. What if this measures your density at a particular point?
Very quickly, could you move up the paper? I don't think we can see what.
Sorry, yeah, let me see what you guys are looking at. Yeah, okay, I see it now. Yeah, so in this integral, if this function is measuring the density of whatever material this cylinder is made of, this could be some alloy that has varying densities. Well, apparently it would have a density of 0 if you happen to be on any of the coordinate planes. That seems a little weird, not to mention the negative density. But anyway, if you have a function that represents the density at each point, if you multiply the density in that region times the volume of that region, you'll get the mass of that little chunk of the cylinder. And if you add up the contribution from each little chunk, you'll get the total mass of the cylinder. So this would calculate for you the total mass of a cylinder whose density was varying at each point. Does that give you an application as to why you might want to compute such an integral?
Yes, thanks. I understand it now.
Okay. And now, Yang Zhu, you did have a hand up. Oh, I'm sorry. That was, wait. Somebody else. Yeah, oh, that's right. It was Sohaib.
Yes. How did you find the limits of the x-coordinates on the unit disk?
It wasn't on the unit disk exactly. I got the limits of the y-coordinate on the unit disk by asking for the northernmost point and the southernmost point. When it comes to the x-coordinates, I'm only finding the min and max not on the entire disk, but just on the line segment on which the y-coordinate was held constant. And my method for doing that was to say, okay, I darken in the points that I think are the winners first, and then I ask myself what I know about these points. Really, I should have said that there's 3 things to know about these points. They're points in 3-dimensional space. I should really be drawing everything in this figure over here, but I know it's a very crowded picture now. Here's that horizontal line segment. And this little point has 3 coordinates, x, y, and z coordinates, but I know 3 things about it. First of all, it's in the plane where the first variable z was held constant. So it was in a plane. And then I next held the y-coordinate constant. So I'm within that plane, I'm down to just having a line. And of all the points on the line, the only ones that are inside the cylinder are the ones that are on this line segment. And the one that has the least or the greatest value of the x-coordinate, those will be ones that actually pierce the edge of the cylinder. So They have a fixed z coordinate and then also a fixed y coordinate. But then to determine the x coordinate, use the fact that you're on the cylinder, so the equation of the cylinder applies. If you knew the z coordinate and you knew the y coordinate, because those two had been held fixed, the only one that's left to determine is the x coordinate, and I can take this equation and solve for x. Well, there's two solutions, one for this point and one for that point. But those are the x coordinates of the points that have, first of all, the fixed z coordinate, and secondly, the fixed y coordinate. And now you want to know their x coordinate, but you observe that they are points that are on the edge of the cylinder, so the equation of the cylinder applies.
Okay. I see. Thank
It
you.
takes some doing. Fortunately for you guys, we're not going to do very many three-dimensional integrals, but I do want you to see that they can be computed without any real change in the theory. Hey, listen, I'm trying not to go over, and I know I did, but I wanted to take your questions. Let me repeat what I said at the beginning of the hour. On the homework, you're only going to be responsible for the first 6 questions for right now. The other questions, you won't really be able to answer them until we get through next week's material. So I've pushed the due date back on the homework. It's not due until April 15th. Okay? Oh, Youngji, you have another question or comment?
Yes, I found out that when we like integrate this integrand in another order, like inside is dz and dy, then dx, and then for the boundary of z, we still have -1 and 1 instead of like some random expression in terms of x.
Yes, that's true in this particular problem. That is true. Yeah, so I don't know, you went through the whole process? That's good. So if you do it in this order, he wants dz on the inside, dx on the outside, dy in the middle. The minimum and maximum values of the x coordinate are indeed -1 and +1. The y coordinates would, when x is held fixed, then the y coordinates can vary from negative the square root of 1 minus x squared to positive the same square root. And now, when you hold x and y fixed, and you ask me what the range of values of z is, turns out it's just z equals -1 and +1, irrespective of which x and y you've already chosen. In the picture, you can actually see that if you fix x and you fix y, then you're down to a line that passes through a certain point in the xy plane. You tell me what the x coordinate is, you tell me what the y coordinate has to be. Now you're stuck on a line that's parallel to the z-axis. And within this cylinder, that line intersects the cylinder in just a line segment. The highest z-coordinates up here, the lowest z-coordinates down there. But if you ask these 2 points what their z-coordinates are, they're just going to give you numbers. In this particular problem, it doesn't depend on x and y. If the top had been, you know, a part of a sphere or a slanted plane or I don't know, a cone or something like that, then the maximum z-coordinate would depend on x and y, and so you would see some formulas involving x's and y's in these spots. But no, you're right. In this particular problem, you have constant limits of integration on the inside. Just so you know, if you then start to do the integration problem, when you integrate z, or a constant times z, as z goes from -1 to +1, you'll discover this integral comes out to be 0. So the whole integral is 0. And that didn't matter to me too much. I just wanted to focus more on the limits of integration, but hey, you might as well complete the integration calculation. All right, guys, I'm going to cut it off because we've gone an hour. So thank you for coming, and listen, we'll see you on Monday, but between now and Monday, stay safe. Don't touch too many people's hands. Wash your own hands frequently. You know the drill.
Absolutely. Thank you so much, Dr. Essen.
All right, and we'll see you guys on Monday.
See you Monday.